Good evening, students. So today this is the second lecture on principle of band structure. Okay. So last time what we have started that how to form matrix equations or how to solve matrix expression from Schrodinger equation. In brief, like this is our matrix expression. Schrodinger expression that you can find out E phi r is equal to h del square 2m del square plus u phi r. Okay. Now there's one of the popular method to solve this Schrodinger equation to compute to consider basis function. And normally what we have done, we always consider the atomistic basis function. Like if it is a hydrogen, it's a good approximation that you can take like 1s type of basis function. There are many basis function like sine basis function, cosine basis function, Gaussian basis function, lot of basis function that you can consider. And UMR, this is actually kind of basis function where phi m is nothing but numbers or coefficient. It looks like that UMR, the basis function you know, and now if you know that phi m, that is called a coefficient, then you can reconstruct your wave function. That's the idea. Now what happened, if you actually recalculate, like if you put it back to your original Schrodinger equation and recalculate it, you'll get this expression like Es phi is equal to H phi. Okay. And those people who are doing first principle method, they will try to compute each and every component of S and phi, and how to calculate that each and every component of S and H, like S and M is equal to the UM star UNR or H and M is equal to UMH UNR. So H is kind of operator here, but here we are actually considering what is called the semi-empirical method. What is that? Like we ultimately get E phi is equal to H bar 5, H is, and and we are trying to what is called adjust the each and every component of this H matrix so that we can get a best fit of our experimental data point. That's the idea. And based on that concept, we have studied how to calculate the hydrogen. That EK diagram of hydrogen molecules, okay, and that you can realize, and that you can study my first lecture, and ultimately we got the EK diagram which looks like that E is equal to epsilon plus 2t cos Ka. Okay. Now the question is it that necessary to solve this Schrodinger equation each and every time, or it's very complicated method? Understand, like we need to have a Schrodinger equation, then we have to transfer it to a matrix form. From that matrix we have to somehow try to look that experimental data point, that is true, and now we try to adjust my H, that is also true, and we have to do a lot of things. Like we really need to solve the matrix each and every time. No doubt that is a good method, but is it that only one method available? Is there anything called what is called the most easy method? Is there any easy method to solve this kind of expression? Okay, that Schrodinger equation. Yes, there is one easy method is available, which is very I think handy also. Like the main principle is that convert the matrix expression to algebraic expression and try to solve and try to get a general expression. With this general expression, you can solve not only even 1D, 2D, 3D, whatever lattice problem, which is really handy, because you understand, like if it is a 3D crystal and if you try to find out the EK diagram and if you try to form the what is called the matrix method, it's a really painful method. Not only for you, it's also painful for the computer also. So we should avoid normally. So this is the lecture what I am going to discuss about the general method to solve Schrodinger equation. Okay, and actually this is a method that I am going to solve each and every time. Okay, and this is the method I am going to use each and every time. Okay, and that is very handy. Even almost analytically you can you can write all the EK diagram. Okay, so let's start from how can get that general method. So this is our original expression that you can find U phi is equal to H phi. That is actually matrix equations or expression. Now, if you have a matrix expression, if I think if you can remember the linear algebra classes, okay, the 10 plus 2, even the BTech undergraduate courses, then there is method. As you know, that matrix is nothing but a set of called a algebraic expression. Okay. Now the question is, can I transfer matrix equation or expression to algebraic expression? Yes, it is possible. Okay, and it is very standard theory available. You just go back, check Wikipedia or check Google. You can do the Google. You can get that expression. Okay, or even eventually you can. You can also think, you can write some matrix and try to convince yourself this is correct. So what happens? So what I am trying to put here, that nth component of phi. So you see that here is my E phi is actually called my column matrix. H is actually n cross n matrix, whatever. Okay. Now what I am trying to understand, phi is a column matrix. You can ask, so what is the nth component of this column matrix? That is my idea, and you can see this is the algebraic expression. E phi n is equal to summation over m. So you understand, no, that we need to add the m component. If you go back and check the matrix multiplication rules, so you see that it is not only that Hn, and we need to add the mth component always. So that means my sum, and that has to be added. So this is my summation over m. Okay, and then phi m. Okay, that is actually transferring my matrix expression to a algebraic expression, series expression. Okay. Now this is kind of if we have, so what is the benefit? Let us see what is the benefit. Now you can see what is, just look at this solution. As we remember our last day, what we have done for the matrix method to solve hydrogen molecule problem, that we have some E phi n, epsilon phi n, T phi n minus 1, T phi n plus 1. That is my algebraic expression we got, and then what we did, we actually assume some possible solution, and that is phi n is equal to phi 0 e to the power I n k a. And look at that, this solution is good only in one dimension case, but since here we are discussing about any dimension, like it may be one dimension, it may be two dimension, it may be three dimension, any dimension. So what we have to consider a general expression. So this is, you understand, this is actually a solution for one dimension, and this is that what we have a general solution, that is actually any dimension. Okay, so phi n is equal to phi 0 e to the power I k. K is actually here vector, and dn. D is actually, I'll show you what is the dn. Dn is actually distance. So look at that, what is dn? I'm just just consider that it's a two-dimensional crystal, right? One here actually almost 12 kind of lattice points are there, and assume any atom. Suppose it's the nth atom. Okay. Now, what is the distance between this nth atom from the origin? That is called the dn. Now you may ask, where is my origin? Okay. So my answer is the origin may be anywhere. It doesn't matter. Why it doesn't matter, I'll show you in a minute. But as an example, I have taken origin as here, and what is the distance from origin to here? That is actually dn. Okay, nth component distance from the origin. Okay, that's the distance. And k, if it is a three-dimensional, because maximum we can have a three-dimensional crystal, so kx ky plus kx plus ky plus kz. Okay, that's the my solution. Now what is the main idea of the solution? If you have this solution, what you have to do, the phi n value you have to put it back to equation 3, this expression, and try to find out what is my energy, and that is what I have done here. So there is some typo here, so let's correct it. It's instead of 24, it is actually 4. Okay. Okay. So here actually, so what I have done, so E phi n, H and M phi m, here is that. So I actually put it back over here. So H and M is so phi 0. Now here is, you see, this is a phi m component. Okay. So we have to replace n by m, so like that. So you understand here, no? Like if it is a nth component, means phi 0 e to the power I k dn. If it is a, suppose, second component, phi 2 component, means phi 2 is equal to phi 0 e to the power I k d2. If it is a third component of wave function, that means phi 3 is equal to phi 0 e to the power I k dot dn. Since we have to calculate phi m, so that means it's a mth component. So phi m is equal to phi 0 e to the power I k dm. And that's what I have, I k dm. Now what is my E k? Okay, function of k. So that I k dn will come this side. Okay, this I k dn will come this side, and you will ultimately get h and m e to the power I k dm minus dn. So it looks like that some sort of vector subtraction is there. Here dm minus dn, some sort of vector. Now what is the representative? What does it mean by dm and what does it mean by dn? Let me explain it to my next PPT, next slide. But what I am trying to tell you that this expression, or this expression, is very fundamental, salient expression, and this is called the principle of band structure. Almost everything, whether it's one dimensional, second dimensional, two dimensional, three dimensional, whatever complicated crystal lattice comes, you can easily kind of find out EK diagram. Can you remember our first semester courses? Like if you know EK diagram, you can calculate everything, correct? Can you just EK diagram, from the EK diagram we have calculated mobility, we have calculated velocity, that is called the thermal velocity, we have calculated density of state. All parameters you can calculate if you have a EK diagram. Okay, so here is also the same thing. So this is actually general formula for EK diagram. Now what is the benefit of that? Benefit is that whatever we have done last couple of lectures, maybe last 20 or 25 lectures, what I was trying to give a full expression, full confidence that how history has progressed, how that method of solving Schrodinger wave equation actually tackled. Okay, and ultimately you get this actually as the final expression, and with this expression you really don't need to solve Schrodinger wave equation. Whatever complicated lattice, you just apply this formula and you will get the answer in a minute, not even hour and hour of computer simulation. That is the benefit. So let's see how to apply this formula for 1D, 2D and 3D crystal. Okay, and then I think everything will be clear. So first I'll take 1D lattice, because why we have taken 1D, why we are starting from 1D lattice, because just previous lecture we have solved the EK diagram of hydrogen, that is nothing but one dimensional hydrogen, by matrix method. Means Schrodinger wave equation, you convert it to matrix method and you did something and we get that EK diagram. But it takes actually huge time to solve such a thing. Now the question is, with this formula, just now whatever we have tried, can you get the same EK diagram quickly? Okay, in a minute or 5 to 3 minutes. That's the thing. So we have to understand few things before we apply those formula. We'll slowly start. Okay, let's start. So first, what you have to do, you have to consider an array of one-dimensional crystal, one-dimensional lattice point. That is done. You take any arbitrary point and consider it is a nth point. So here actually I have taken, this is my nth point. So if this is my nth point, so this is my ni minus 1 point, and this is also n plus 1 point. Okay. Now look at here carefully. So as you have must have the good concept like this nth point, what is the energy over there? Epsilon. No, I don't need to explain here, because just go back and check why nth point lattice point has the energy epsilon, because you can understand it if you consider a basis function over here, and if you multiply the same basis function with this atomic point, you will get highest energy, and that is called the epsilon. No, that we have studied last time also. Like I have shown you, like you have a two-wave function. If they multiply each other, you will get the best. But if it is separated by few distance, you won't get uh, overlap area, right? So like that. So just for to have a more discussion on it, like here you can see h11. So you see the same wave function is multiplied by the same wave function h11, and here actually I'll get a highest energy, and that's what I have represented h11. Similarly h12, that is nearest neighbor. You have a h1 and you have a h12. Okay, the next, so h1 and next atom is number 2 atom. And what is my overlap area? This is my overlap area. My overall and this thing we are representing T, that is H&M component of these things, this overlap area we have represented T. Now what is the value of T? That also we have calculated I think 2-3 lectures back. Just check your notebook. What is the value of T here, like H1 or component of H12 or H23 or H34, doesn't matter, because all are actually periodic lattice, and it means that the wave nature of atoms of any position is the same. So 2, 3, if you try to find out the wave component of H23, it is exactly same H34, as long as it is sitting next to each other, right? But the problem arises like here H13, so like 2 is missing over there. So what is the overlap area? There is no overlap, because H1 is here. So H13, the component is 0, because wave function, one wave function is here, another wave function is there here. No, so definitely there is no overlap area, and so the contribution of H13 is 0. Here also we have done the same thing, right? So what we are trying to understand, so this is my nth matrix, okay, and let's always see that nth has the highest value of that component, that is H component. H means the Hamiltonian component, and matrix component, and that is we have represented as epsilon. Now how this nth component is related to the nearest neighbor, so how this nth component related to nth neighbor, so that is H12, or so that is related by the component called T. What is the value of T? Again I am telling you, you just go back my previous lectures, you will find out the T component, okay, and similarly epsilon component also. Similarly, if it is the other way, n plus 1, how it relates to each other, n to n plus, that is T, because they are the nearest neighbor, okay. So the relation between here and here is all the same. Now you can ask that why it is n, why not here? You can definitely consider the nth component here, doesn't matter, because as I told you, it is a periodic lattice. The atomistic behavior is same in the periodic crystal. So you can consider anywhere in this periodic segment. Okay, now I have to do the summation. So I have to do the summation for the 3 term. See, m has to be 3. Why? See, look at that. You just go back and check. We have to do the summation. Let's write this summation here for that. This is the summation. Okay, so I have to do the summation over m. Now So that M is having, so M is having three component. M, when M is equal to N, that means the wave function is multiplying with the same wave function, and nearest neighbor. One is N plus 1 and N minus 1. We don't need, definitely there is a M, maybe there may be another component you can consider, like M is equal to, N plus 2. But we should not be, we should not consider this thing. N plus 2 means like N plus 2 means, so this is N and you are considering these atoms. This is N plus 2, 1, 2. So this atom is 2. So that is actually far away from the N. So this wave function and this wave function, the component H12 or Hn2 is actually 0, because even there is a wave function, there is also wave function, but they are not crossing to each other. There is no overlapping point, so this component is always 0. So there is no point of considering Hn plus 2. So that is why I have written the component called the non-zero component. There would be lot of zero component, but we don't bother about the zero component. We need to bother about the non-zero component. Here you say Hn will give you non-zero answer. So definitely when Hn multiplying by M is equal to N, you will get a non-zero. Similarly, N plus 1, because it's the nearest neighbor of N, so you will get a non-zero, because there may be some overlap zone will be there. Similarly, there would be another N minus 1. Okay, so that is actually 3 summation point. We have to do the summation over M, 3 summation point. Now we can take any arbitrary 0. You can see I just have taken the 0 because I have to calculate dm minus dn. Now how to calculate? You have take 0 over here. Okay, then so this is dn, so this say nth component, this is dn. Okay, and now I want to calculate the component of ek means energy value corresponding to n plus 1. So that is actually m. Okay, this is actually m, dn minus d, this is m. So this is nth component and I have to do the summation over n plus 1. Again I am refreshing it. So this is my nth component and I have to do the summation of n plus 1. Correct? Now, so this is actually my, I have indicated is dm. Now what is my dn minus dm? This is the dn minus dm, right? So it is simply vector summation rules. Okay, and now you see that from here to here it is nothing but a lattice constant, no? The separation between one lattice to another lattice, and we know this dm minus dn is equal to a. Correct? So that's part. So let's write all these components carefully. So n plus 1 component of a. So I am just counting n plus 1. Hnm e to the power ik dm minus n. By the way, what is the Hnm? You know how the n relates to n plus 1 nearest neighbor. So this Hnm is nothing but t. Correct? And again I am telling the matrix component of nearest neighbor we are already calculated. Just go back and check your notebook. Okay, so how that t? So Hnm is actually t. I have not written here. Maybe I have written in the final expression. We'll see in a minute. So Hnm. Now e to the power ik dm minus dn. Now what is k? K is equal to, as I told you, kx plus ky plus kz. And this is a dot product. Okay, dot. And now what is my dm minus dn? So k I have expanded kx plus ky kz. And x, here x, y and z are actually unit vector. Kindly check it again. X, this y and this z are unit vector. It's a bold letter. Okay. Now dot, what is dm minus dx? It is a. Distance is a dot a and x is equal to unit vector, because here it's a positive direction. Here it is a positive direction, so it is plus x. Okay. Now it is simple. It is a dot product, so you will get a ik dot ax or ikx. There should not be any there is some error is there, so I have to correct it. E to the power IKA, not X. So that is the kindly do that typo here. So we have to correct it. So how to correct it? I don't know. Just 1 minute. Let me correct it because it's giving bad. Oh, sorry. Should be IKA. So now it is correct. So you understand that error is actually once the dot product is over, so there should not be an X component because X and X actually unit vector. Okay. So this is actually uh, your answer. So this all the dn, this is dm, so this is actually dm minus dn, that is a, and we have written this part, correct? So this is actually your m product e to the power ik. So why? Because as I told you, this is a simple dot product, so we don't have any component in qi and kz, so that product is 0, only xkx dot ax. So x are its unit vector, so again it should be IKXA, but since it's a one-dimensional crystal, so it is only one K is there, so I can write IKA. Okay, if it is a convenient for you, you can write KXA also, doesn't matter, but I have written IK. Now let's go for the another part. So we have done the summation corresponding to n plus 1 component. What's about the n minus 1 component? Again, you have the series of n plus. So how, and this is actually nth component and the energy is epsilon. How it is related to n, to related to n plus 1 is actually t. Similar nearest neighbor n to n minus, that is also t, that we have related, and you take an arbitrary 0 anywhere and then you write dm, and this is. So here actually you see dm minus dn is other direction. So here the arrow that is it is coming from a positive direction, here it is a negative direction, so minus a. So what is actually that in summation over the n minus 1, that means e component over n minus n, it's like IKA. Now you see that dm minus dn, it matters. So it doesn't matter where is my origin. Origin may be anywhere. It doesn't matter. Matter is only dm minus dn. That's what I told, the origin doesn't matter. Origin can be anywhere. Matter is only dm minus dn. So relative distance. So that is why origin, you can consider it origin here, or you directly go for dm minus dn. That is also fine for us. Okay, so that is good. So dm minus dn is minus a. You do all the calculation, you ultimately get hn e to the power ik. Now let us write the original expression. So ek, now you have to do summation over n. So summation over n, as I told you, that is the value of epsilon. So we'll put epsilon over here. Summation, another component over n plus 1. So sorry, not summation. It's sorry, my words. So we need to have three component and we have to add it. That is the meaning of summation. So we have one component corresponding n, and that is the epsilon. Okay. Since there is a summation, so we have to add, that means it's plus signs, and we have to add n plus 1 and n minus 1. What is the energy component of n plus 1? That is Hnm e to the power ik. What is the energy component of n minus 1? That is Hnm e to the power minus ik. Since there is a summation, so we have to add all these things. Now what is the Hnm component of n plus 1? That is T. We have replaced Hnm by T, and ultimately we'll get all this answer. So epsilon 2T, and you do all this calculation, you get epsilon plus 2T cos Ka. Now look at this carefully. This is the same expression what we got directly from that called matrix formation. And it is simple that you write that formula and you apply this formula, you will get the answer in a minute. Just for an example, I take you into the two-dimensional figure. You will get that EK diagram of two-dimensional lattice in a minute. Just consider two-dimensional lattice, and we need to consider nth component over here. So this is, so since a nth component, so I have to have a epsilon over here, and since it's a two-dimensional lattice, so how many k you should have? Kx and ky, correct? Two dimension. Okay, so let's consider the nth component. So what is the component of H matrix? That is epsilon. Okay, and how they are relating to the nearest neighbor? That is T vector. Sorry, not T vector, T component. This is T component, and Y direction also T component. They are relating to each other. Okay, now you consider 1 0 point over here, and this is, as I told you, this is dn, this is dm. Okay, now if this is my x-axis, so dm minus dn is equal to a. Okay, and we have done this is, so just now previous days, because you consider this is my x-axis, that one dimensional figure. Here you just take one dimension over here, so you'll see this is exactly what we have done just now. We have done it by one dimensional figure. So this is the same thing what I am looking for it. So this is one dimensional, this is kx. So first what is my EK diagram? First epsilon, you have to take epsilon over here because nth point. Now this is my ax. This is my ax. So t to the power ikxa, and this part is equal to t to the power minus ikxa. Now what's about this one? It's actually positive y direction. Okay, so what is the component of k here? It is ky. So ky, and what is the lattice constant a? So that is kya and e to the minus ky. So this is from here to here. That is ky. And if you do all this calculation, you will get 2t cos epsilon, 2t cos kxa plus 2t cos kya. That is actually for your called the EK diagram of two-dimensional lattice. And remember, to calculate the EK diagram of two-dimensional lattice, we have not considered any type of Schrodinger wave equation. We just have taken the formula, apply there, and immediately we get the EK diagram. Definitely you have to do little bit of more work, that is to find out epsilon and t, but that is common for matrix expression also. But from the matrix expression you cannot get this type of expression so quickly. You need to struggle a lot. But here with this formula you can get that EK diagram is very, very quickly here, and that's what I am representing this method as very handy method, and we will be using this method very often as a solution of Schrodinger wave equation. Okay, not through the matrix method and do all this kind of summation and all these things. Okay, that's not weird. That's not a handy process at all. Okay, now there is something that I want to discuss further. There is called the first nearest neighbor and second nearest neighbor. What is called the first nearest neighbor? So it is again the problem of two-dimensional. I just want to tell you the how easy to handle it. The same problem, what is the problem I'm telling you? If you want to handle it a matrix pattern, you have to struggle a lot. But here it is within 1 minute you can calculate. So let us look at, this is my two-dimensional crystal lattice, and here I have to calculate what is the first nearest neighbor. So this is my nth component, and what is my first nearest neighbor? Just consider my green part. First nearest neighbor atom. So the green, just look at that. This is, you can consider any nth position. Now this is my, just consider this is my nth position, and what is my first nearest neighbor? This is my first nearest neighbor. Okay, and here you consider this one, this atom, or this atom, or this atom, or this atom. We have not considered. Okay, we have considered only this one, just first nearest neighbor atoms. Now the question is, for this two-dimensional figure, see, one dimensional we don't need to consider. No, one dimensional I really don't need to think from the contribution of these atoms and these atoms. Okay, because it is separated by the n-1. From the contribution from here to here, it is far away, because this atom and these atoms are far away. So wave function of this one and wave function of this one is far away. So we really don't need to consider this one and this one. But the moment you have a two-dimensional figure, it's not about the first nearest neighbor we have to consider. We may need to consider the second nearest neighbor. Remember the word called second nearest neighbor. Now the question is how to write the EK diagram here. So EK diagram combining first nearest neighbor plus second nearest neighbor. Correct? Now if it is the first nearest neighbor, what is the solution? You know that I have written the solution directly. So just that is the, we have just now got, no? So just 1 minute. This is the solution of first nearest neighbor, right? If you have a first nearest neighbor, so epsilon 2t cos kxa plus 2t cos kya. If you have a first nearest neighbor. Now here actually I am telling you what's happened if you have a second nearest neighbor. So this is the solution of first nearest neighbor. Epsilon 2t cos kx plus 2t. That means if you have considered the green part, that is the solution. Now I have to consider one of these all atom, like atom number 10, atom number 12, atom number 4, atom number 12. So how to calculate these things? Okay. So this is my, so that means from the distance from dn to dm we have to calculate. Remember, in this case I am not drawing anything 0 0. As I told you, 0 0 could be arbitrary position. Only thing is matters like dm minus dn. It matters only dm minus dn. So I have, this is my dm. No, this is nth position and this is m position. Okay, so dm minus dn. Now the question is, what is the value of dm minus dn? That we have to calculate. So it is very easy to calculate, because this is what. So this line, if you say it is, I think it is a sky blue. So this line, it is minus ax, because this moves this direction. So it is minus a, and x is actually unit vector. Okay. And now we have to consider this one also. This is actually ay, right? Because from because it's a unit, is a periodic crystal, so all the distance between one atom to another atom is a. So I have considered a, and y is the unit vector. So this is actually positive y direction, and this is minus x direction. Now if you know this one and this one, so what is dm minus dn? This is minus ax plus ay, right? This is simple vector addition. So that means what is my contribution over here? The contribution here, okay, here actually one thing that I have forgotten to tell you, like as I told you, like 1 minute. Okay, so the relation between the first nearest neighbor, that is n to 11, n to n plus 1, n to 3 or n to n minus 1, we have written as t. Okay, but if it is a second nearest neighbor, that is hn to 10 or hn to 12 or hn to 4 or hn to 12, let us write t1. What is the value of t1? Again you can calculate, and that's your homework. Just go back and check at least 4 or 5 lectures before I have calculated all these things. So go back and check. Okay, so if you know the atomic position, you can easily calculate the H, each and every component of H matrix, correct? So you know that H12, that Hn12 or Hn10 you can calculate. So that is called the relation. Okay, so here nearest neighbors is related by T, and here second nearest neighbor, it is supposed related to T1. So that is why HNM here is actually T1. Okay, and what is the value of dm minus dn? And that is actually x plus ay. Okay, then if you, and k component is simply since a two-dimensional crystal, the k component is actually called kx plus ky. So if you multiply it as a dot product, so you can get the right answer over there. Okay, so this is actually, as I written, EK diagram consists first nearest neighbor, this one. So what's about the second nearest neighbor? So that is, you look at that atom number 10. If you consider the atom number, this is atom number 10, so this contribution will come. If you consider atom number 12, so this one, so this contribution come. If you consider atom number 2, okay, because these are the second, black atoms are actually nothing but second nearest neighbor. So this will come, and finally this one. So once you have all this component, now you have to do some algebraic manipulation, and you get, finally you get, this is the EK diagram. Now you see, if you would have applied this method by this conventional solution of method, like solve the Schrodinger wave equations, and how to solve it, you have to write the matrix, you have to find out all the component, and if you do all these things, so definitely it will take more than an hour at least. But here within few minutes you can calculate the EK diagram. Okay, and this EK diagram is actually nothing but the first step of a band structure. I'll say first step, or it is some people, some scientists say this is actually called the band structure. So I'll say it's the first step of the band structure. Okay, and you know, if you have a EK diagram, you can calculate everything. So somebody, if you say like, okay, what is my EK diagram? What is my mobility? You can calculate here, no? Or what are the relative velocity? Okay, that you can calculate. Okay, all these things that you can calculate. Or what is the density of state? You can calculate. So if you cannot calculate, don't worry, because I am going to discuss this thing in a detail, how to calculate it. Now here actually one thing is missing, that is how we have considered the atomistic basis function. Okay, just remember our first semester discussion. To convey Bravia lattice, there are lot of lattice points are there. Okay, and if you combine one or two atoms together with a basis function, this get the solution, it is easy to get the solution, correct? So how to, here actually till now I am considering single atom, single basis function. I have not considered SPD or all these things, right? Now if we can do it, so how to do it we'll see later on, then I think it is much more easier. Okay? So that is I am going to discuss next day. And your homework is actually compute the EK relation of 3D lattice, consider periodic lattice crystal in all axes, because this is the starting point of finding the EK diagram of silicon. Okay, so thank you. So hope you are safe, and I'll be uploading a video lecture again regarding the called the multiple basis function, how to handle the multiple basis function. And with this thing I have to little bit correct the formula like HNM, like EK is equal to summation of HNM and UM, that formula I have to reduce, that is principal band structure formula. If I can calculate it, if I can modify it, that is the complete expression. And with this expression, within minute you can calculate EK diagram, and that's what we need. Okay, we need it to find out the density of states. Okay, thank you.